on the last page, we're just doing some simplification of trig expressions and also using the law of sines and cosines. For the trig expressions, remember our philosophy was to take the expression that I have, so taking just this side, changing everything in terms of sine and cosine. So if I do that, then instead of tangent theta plus cotangent theta, I have sine theta over cosine theta plus cosine theta over sine theta. To simplify this, I need to, if I want to do this addition, I need a common denominator, and so the common denominator here will just be sine theta times cosine theta. So in the first problem, or the first fraction, if I multiply the top and bottom by sine of theta, I'll have sine of theta times sine of theta, and in the denominator, I'll have sine of theta times cosine of theta. And then in the second fraction, if I multiply top and bottom by cosine, I'll have cosine of theta times cosine of theta, again, over sine theta, cosine theta. So I have rewritten each fraction, not changing it, just rewriting it, so that now both fractions have the same denominator. And so now I can combine the two fractions over that denominator and realize that when I write sine times sine, that's really just sine squared. And when I write cosine times cosine, that's cosine squared. Our Pythagorean identity now tells us that sine squared over cosine squared is 1. So I have 1 over sine theta, cosine theta. So that's my simplified expression for the left side. For the right side, right-hand side, secant of theta times cosecant of theta. Again, I rewrite this in terms of sine and cosine. Secant is 1 over cosine, and cosecant is 1 over sine. And so when I multiply two fractions, I just multiply the numerator, multiply the denominator, and I'll have 1 over sine theta, cosine theta. And so the point about establishing identity is that those two things are the same. So the simplification is the important thing. If you can show that two things simplify to the same thing, then obviously that shows that those are originally equal. So in this problem, we'll have the same sort of thing happening. We have secant x minus cosine of x, and so we replace secant with 1 over cosine. To get a common denominator, so I'm rewriting this second expression, the cosine x, as a fraction over cosine x. So multiplying this guy, top and bottom, by cosine. That's how I'm getting this guy. But the numerator of that new fraction is 1 minus cosine squared, which our identities tell us is equal to sine squared. That's the Pythagorean identity again. And so that's really the same thing as sine of x times sine of x over cosine of x. If I split that up, and the only reason for splitting it up is that then you can see that it really is equal to sine of x times tangent of x. So it's not too hard to see that these two things are the same. But really this is the point, is that if you started with secant of x minus cosine of x, it simplifies to sine squared over cosine. The last two problems here are just problems using the law of sines and cosines. We know that if we have two angles in a triangle, we automatically know the third angle, so the other angle will be 110 degrees. And we learn that if you give me all the angles in a triangle, then the law of sines is useful for finding the other side. So I'll just label this side x, and the other side you would do similarly. But the law of sine says that the sine of 110 degrees over x is opposite the 110 degree angle, is equal to the sine of 30 degrees over 8. 30 degrees is opposite the side of length 8. And if you solve this for x, you can cross multiply or solve it however you want. You'll get the value of x. Looks like it's 15.035, something like that. And again, you just use something similar to find the side over here, also using the law of sines. In the second problem, there's a little more going on. We do need to find this other side, and that's going to be the law of cosines. So let me write that down. C squared is 6 squared plus 10 squared. Remember, it feels just like the Pythagorean theorem, but then we have to subtract 2 times 6 times 10, and I'm running out of room, times the cosine of the included angle, so cosine of 45 degrees. So this becomes a bit of a more difficult calculation, but as long as we don't lose the fact that that's c squared, we should be able to do it. So according to my calculator, the stuff on the right here becomes 51.147, which means that c is approximately 7.15. So the side that's here, the side C has length 7.15. The harder part, or not harder part, but the part that doesn't just come directly from the law of cosines is try to find out what these angles are. So this one and this one. We will discuss in class, I don't think we have yet, but we will discuss in class what's risky about trying to find this angle that's close to 90 degrees. The law of sines is really bad at this. The law of sines will not be able to help us find an angle that's greater than 90 degrees, because when we use the law of sines to find an angle, we need to use the inverse sine function, and the inverse sine function does not ever give an answer back that's in the second quadrant. So the inverse sine function is not capable of returning that as an answer. So for that reason, it's a lot safer to label the angle that we're sure is the smallest angle. We can tell that's the smallest angle because it's opposite the smallest side in the triangle. And then we can use the law of sines to find that. So I know that the sine of A over 6 is equal to the sine of 45 degrees over C. Remember, C was 7.15, whatever it is. So the number we just got. So that means I would need to multiply both sides by 6 and then use the inverse sine function. And if you do that on your calculator, again with your calculator in degree mode, in this case, you'll get that angle A here is about 36.4 degrees. And just as we mentioned before, once you know two angles in a triangle, you automatically know a third angle, right? You automatically know the angle on the other side, because you'll have to head up to 180. And if you check, this really is bigger than 180, and so the angle that's over here, we would have had trouble using the law of sines to find that. And if you're not sure what I'm talking about, try it. Try doing exactly the same thing we just did with that angle, and you'll get an angle for B that doesn't quite make sense. So in terms of the triangle adding up to 180 degrees. So anyway, so we do need to work some more on these kinds of problems that involve finding angles. There are some tricky things that happen there. The problems like this, where we have the angles given, are much more straightforward.